Thank you for joining me for this video where we are introducing you to the concept about absolute and conditional convergence. Two terms I've never talked about, but now we should. Absolute convergence implies true convergence. Conditional convergence does not imply true convergence because that is a situation where you could see divergence as well. We are looking here at a bunch of rules, two of them, then we're looking at these symbols. If you're looking at something which looks like this, a absolute value with regards to a series from n equals some value up to infinity, you would have terms such as this. You would have 1 over, and I'm just being hypothetical here, 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. You see how everything here is positive? If I'm looking at something which looks like this, now in this particular instance we could be looking at something which is 1 over 2 minus 1 over 3 plus 1 over 4 minus 1 over 5. You see the difference? Here the absolute value converts everything into positive. Here the not absolute or the absence of absolute value, you can see alternating terms with regards to signs, positive and negative, all of that shows up. Keeping that in mind, now let's look at that very first rule because it's very important. If you have a particular series which looks like this, complete absolute value, complete positive terms, everything here is positive, and this were known to converge. In this particular instance, if you know this to converge, then its counterpart, which would be this without the absolute value, where you could see a1 minus a2 plus a3 minus a4, all of that, then this would also converge as well. In this particular instance, we're looking at a case of absolute convergence. If the sum of the series where all the terms are positive converges, then its counterpart where you don't have the absolute value, then you have absolute convergence with regards to that. And why would that be the case? Well, it would be the case because if you can prove that all the sum of the positive terms are giving you convergence, then where you have alternating terms, positive and minus, you must definitely have convergence because those negative terms only take away from the total sum of the series and help you come towards a more finite value. Therefore, you definitely see absolute convergence. This here is just a very basic and generic example of that rule 1. Now everything with regards to the reverse comes into play with this rule number 2. According to rule number 2, if you have a situation which is this, and let's say a1 minus a2, a3, and then we'll say here minus a4, we're looking here at the not absolute value where you could have a combination of positive and negative values. If this were deemed to be convergent, the absolute value counterpart does not necessarily have to be convergent, and likely it won't be convergent. And here you would only be looking at a situation of conditional convergence, because just because this is proven to be true, this right here is not necessarily proven to be true, contrary to what was the case with rule 1. Because if you prove this to be convergent, then this had to be convergent. But if you prove the non-absolute value version to be convergent, the absolute value version of that does not necessarily turn out to be convergent. The best you can do here is conditional convergence. With rule 1, you're seeing absolute convergence. With rule 2, you're seeing conditional convergence. And there's also a situation that you need to understand. In the particular instance where you have a sum of these type of terms where all of them are positive, and they end up being a divergent case, then you have a true divergence with respect to that. You'll have a true divergence over there. But we're focusing here more on the distinction between absolute and conditional convergence. These two distinctions have to be kept in mind. Allow me to generate just an example and bring all of this to perspective. It doesn't have to be too formalized. With regards to rule number 1, if you had a series which looked like this, 1 over n squared, and we'll say from 1 up to infinity, you know you're looking at 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16. You know here the p series, the p value here is greater than 1, it's convergent. In this particular instance, you really have a hidden absolute value because all of these terms are positive. You're seeing convergence. If you were to look at the non-absolute value counterpart of this, and we can look at something like this, 1 over n squared, and then we can do here a little bit of a change such that we do minus 1 to the power of n minus 1. Now we're looking at the not absolute value or the absent absolute value counterpart of this, where you can have these terms show up: 1 minus 1 over 4 plus 1 over 9 minus 1 over 16 plus you'll have 1 over 25 minus 1 over 36. You'll see this to be the series. This right here is exactly the same, except you have absence of absolute value. If you've proven the absolute value version to be convergent, the absent absolute value counterpart will also be convergent, but it will be absolutely convergent. That's what the rule is telling you. If you can show this to be the case, to be convergent, then the counterpart without the absolute value is obviously absolutely convergent. That has to be kept in mind. And this example would show it to be the case, because here again the p-value is larger than 1. These minus values would not have any impact, because towards the sum of the series the minus would take away from that and bring you towards a finite value. And this exemplifies rule number 1. Now let me show you rule number 2 in terms of an example, and why it is obviously a conditional case and not an absolute case. Think about this particular instance right over here. A harmonic series 1 over n from 1 up to infinity. Your harmonic series is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. In all instances, this is proven to be divergent. Why is it proven to be divergent? Because here you have 1 over n to the power of p, where p is equal to 1. If p is always less than or equal to 1, it's a divergent case. And you know the basic harmonic series is divergent. In this particular case, we're looking at a series which indeed is the absolute value. All the terms are positive. We're looking at something like this, and it is showing to be divergent. If you were to look at now the non-absolute value counterpart of this, and you'll get the alternating series come out from here. You can bring in the non-absolute version, which will be minus 1 to the power of n minus 1. Here your harmonic series converts into 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1 over 5. Now this particular case, using the alternating series test, each succeeding term is less than the preceding term. The limit as n approaches infinity, this tends towards 0. Here you see convergence. The alternating series test proves it to be convergent, but we're looking here at rule 2. The absolute value version was divergent. The non-absolute value cannot be absolutely convergent, but this convergent can be at the very least conditionally convergent, and you cannot do anything better than that. That's the rule 2 in terms of an example. If you have shown this to be divergent, its non-absolute value counterpart can be convergent, but it can only be at best conditionally convergent. Rule 1. If you've shown this version, the absolute value version, to be convergent, at best the non-absolute value version will be absolutely convergent. And now you see the distinction between the two. And let this video remain at that without me repeating myself, because it's not too difficult to comprehend, but you can see the two cases I've laid out to you individually, rule 1 and rule 2. Rule 1 brings you absolute convergence, rule 2 brings you conditional convergence. Rule 1, you prove this to be the case first, and then you automatically arrive at that. In rule 2, you show divergence with regards to the absolute value version, but the non-absolute value version can be convergent. It doesn't have to be, but it can be, but it'll be conditional. And let's end the video with that. I'll be presenting a video with regards to the same topic, but with good practice examples. Here I'm just introducing you to this concept. Thank you for watching. Have a good day.